Welcome to the second video in this series, Checking Trends, Making the Most of the Joint-Point Trend Analysis Software. I'm Huanshan Chen. I present Section 2, the Basics of Joint-Point Model, on behalf of Joint-Point Model Development Team. What is a joint-point model? Joint-point model is a piecewise linear model with several connected segments. Each segment is linear or linear in log scale. The model is continuous. Two consecutive segments join, and the places where they join are called joint points. At a joint point, the trend starts to change, indicated by slope changes. The number and the locations of the joint points are determined by the data, and the maximum and minimum number of possible joint points are selected by the user. There are a few aliases used in the statistics literature, such as piecewise linear model, segmented line model. Joint points sometimes are called change points or changeover points. This figure shows a data series from 1969 to 2000 and a fitted joint point model with two joint points located at 1973 and 1991 respectively. The red line represented the expected line from the model. There are three segments in the model. 1973 and 1991 are the joint points. This is the mathematical form of a joint point model with two joint points. The dependent variable is y or log of y. The model is shown in the figure. The red line represents the expected line from the model. There are three segments in the model. The first segment has slope beta 1 and intercept alpha 1 between 1969 and 1973. The second segment has slope beta 2 and intercept alpha 2 between 1973 and 1991. And the third segment has slope beta 3 and intercept alpha 3 between 1991 and 2000. The joint points are at 1973 and 1991. One important feature is that the three segments are connected so that the fitted value at the year 1973 for the first and second segments are the same. That is, alpha 1 plus beta 1 times 1973 is equal to alpha 2 plus beta 2 times 1973. Same is at the year 1991. The second and third segments are connected so that alpha 2 plus beta 2 times 1991 is equal to alpha 3 plus beta 3 times 1991. The model we just presented is called general parameterization in the joint point software. In this example, two joint points are in the model. There are 6 parameters and 2 constraints in this form. We usually do not care much about intercept in each segment. We are more interested in the slope because slope represents rate changes. Alternatively, we can reparameterize the model so that the model shows the slopes and the increment between slopes of adjacent segments. The alternative parameterization of the same model is called a standard form in the software. Here is the mathematical form of this model with 2 joint points. There are 4 parameters in the form: beta 0, beta 1, delta 1, and delta 2. This figure further illustrates the same model with the standard form. The first slope is beta 1, the second slope is beta 2, and the difference between them is delta 1. That is, beta 2 is equal to beta 1 plus delta 1. Similarly, beta 3 is equal to beta 2 plus delta 2, which is also equal to beta 1 plus delta 1 plus delta 2. As an example, this is a screenshot of the joint point software output. The top portion uses standard form. There are 4 parameters in this form. The bottom portion uses general form. There are 6 parameters in this form. We use this standard form because standard form needs only one equation for the model. On the other hand, the general form describes the same model by an equation with 2 constraints. Standard form forces the consecutive segments to meet at the joint points. A parameter is used to represent the change of slope from one segment to the next. If the number and locations of the joint points are known, this model can be estimated directly using regular regression program. In the supplemental materials for this video, we will show how to fit a joint point model using regular linear regression software when the joint points are known. In previous slides, we assume the locations and the number of joint points are known, which is relatively uncommon. It can happen when we know some change in the industrial process, such as putting a new equipment, and we know the exact dates of the change. However, in most situations, we do not know the number and the locations of joint points, and they need to be estimated. We will discuss how to find the number and location of the joint points in other videos. To interpret the parameters, assuming that the data is collected yearly, when the dependent variables is on log scale, the slope corresponds to annual percent change, or APC. More precisely, APC is equal to exponential of beta minus 1 times 100%. If the dependent variable is not on a log scale, the slope is annual change in y unit. For example, if y is count, then beta represents the number of count increase or decrease in a year. In joint point, we usually use a log scale in cancer rates. An important feature of APC is that it is a relative metric, so it can be meaningfully compared across a broad spectrum of cancers, from very common to very rare. For example, rare cancer increasing at 2% a year can be compared to common cancer increasing at 2% per year, even though an absolute level common cancer increase much more per year. One thing to keep in mind is that we do not necessarily believe the cancer rates change at a constant rate for a fixed period and then suddenly change direction, but it is useful simplification of reality like all models do. Here is an example of SEER age-adjusted incidence rates for liver IBD cancer between 2000 and 2019. This is for male, white, including Hispanic, all age, all stage incidence rate. The first segment is between 2000 and 2002. From year 2002, there's a statistically significant rising trend with APC equal to 6.7%. The statistical significance is based on level 0.05. From 2005 to 2014, the rising trend is slower with APC equal to 3.4%, but it is still statistically significant. Since 2014, there is a flat trend with APC equal to 0.4%, non-significant. The trend pattern is consistent with the findings that liver cancer rates have been increasing steadily for decades, and the increase in incidence is closely related to chronic hepatitis C virus infection. For interpretation of beta, if the dependent variables is count, log scale is not necessarily a better choice. For example, the figure are for the same data where the dependent variable is count and X is the month. One modeled by log scale and the other in linear scale. The left side using a log scale, so the slope corresponds to MPC, monthly percent change. In the left, we see a large increase between 2018 September to 2020 November, with a monthly percent change of 7.64%. In the right figure, where a linear scale is used, around the same period, we see the corresponds to increasing trend in two segments, one from February 2019 to March 2020, and the other from March 2020 to November 2020. From March 2020 to November 2020, the increase is about 28.36, which means there are about 28 cases increase every month during the period. The main difference between the two figures in left and right is how to interpret the changes. If the data, for example, is the sale of 10 sanitizer cases count during COVID, it may be more meaningful to a company executive to know the sale changes in count rather than sale changes in percentage. In summary, we usually prefer log scale in cancer trend analysis, but it depends on the data and one can use or without use log scale. This model is proven to be extremely useful in analysis and interpretation of health-related and other trends. Further videos will describe the model and its features in more detail. We also provide additional supplemental slides to describe the relation of this parameterization in more detail. Also, we will show when joint points are fixed, how joint point model can be estimated directly using regular regression program. Finally, we will derive the equation for APC. This is the end of section 2. Thank you very much for watching.